Welcome to the lecture on Carnot Principle and Carnot Cycle. In the previous lecture, we had looked at reversible and irreversible processes. All real processes are irreversible, and we had discussed some characteristic features of irreversible processes. However, analysis of reversible processes is very useful for getting bounds on performance efficiency of real processes. So we would lay foundation to the utility of reversible processes in the analysis of reversible engines. That's what we're going to see now. In the next couple of lectures, it'll become more clear how reversible processes will be used for setting up bounds in efficiency and so on. Much of this work was initiated by Carnot. The motivation for him to look at reversible cycles was actually steam engines and heat engines. What he observed was whenever there was a work-generating device, the work-generating device exchanged heat from high-temperature reservoir to a low-temperature reservoir. Okay, so you can also physically imagine what this kind of a device will be like. For example, heat can be supplied here, just the fluid can be just water. Steam is generated here, it moves a piston, and there's a rotary device here, and then there's a condenser, heat is rejected here, and the water is recirculated back. Okay, so this was this observation, a heat transfer from high temperature reservoir to low temperature reservoir resulted in work. The arguments of Carnot are non-mathematical. They're actually logical arguments, proving some deep thermodynamic principles. In fact, it was based on a wrong theory of heat. It is based on caloric theory of heat, okay, so which was later disproved. But at that time, this was debated. So it also shows that you can get you can use a wrong theory to get right results. Okay, so it's all power of logic here. He showed that the reversible cycles had maximum efficiency, and he also proved few other things. We will elaborate in the next few slides. Okay, so one of the things of great consequence is that he proved that the reversible cycles can be operated on a fluid, on any general fluid. Okay, it doesn't matter whether you're using water or air. Okay, so the efficiency of a reversible engine is just dependent upon the temperature of hot and cold reservoir, and is independent of the engine fluid you're using. Okay, so these are all very profound deductions just based on logic. So we will see how Carnot went about proving these principles. So there are two Carnot principles. I'll first state them, and then we'll see how Carnot proved them. Okay. So the first principle is that the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one operating between same two reservoirs. Okay, so there are two thermal reservoirs. This determines the efficiency. You will see if there is a heat engine, one is irreversible, another is reversible. The reversible heat engine, which is transferring heat from high temperature to low temperature reservoir, has greater efficiency. The second Carnot principle is that the efficiency of all reversible heat engines operating between the same two reservoirs are the same. Okay, so it is independent of the engine fluid that's being used. So it just depends upon the temperature of the high and temperature of the low temperature reservoir. So this can be visualized using the schematic. So what we are trying to say the first Carnot principle is illustrated here. If there is an irreversible heat engine and if it's a reversible heat engine, the irreversible heat engine has lesser efficiency. Okay, eta is a symbol for efficiency here. Irreversible heat engine efficiency is less than that of the reversible efficiency of the reversible heat engine. And there's the second principle is illustrated here. Let's say these are two reversible heat engines operating with different fluids. Okay, so you may imagine one is operating via water, steam, and so on. The other is operating via air. Okay, it doesn't matter if the temperature TH and TL is fixed, then the efficiency is one and the same. Okay, so this is a lot of consequence, with, not for just for analysis. You'll also see it's going to be used for establishing a thermodynamic scale that is independent of a thermometric fluid, right? Okay, so let us see what was the logical argument that Carnot utilized for proving principle 1. Okay, so what is to be proved? The efficiency of an irreversible heat engine is always less than the efficiency of reversible one operating between two reservoirs. So let's just set up the problem. There are two heat reservoirs. One is at TH, the other is at TL. H means hot, L means low, right? So that's what these subscripts indicate. So let's first imagine an irreversible heat engine. So QH is supplied from the high temperature reservoir to the engine, and some amount of heat, in this case QL, irreversible, is being rejected, all right, to the low temperature reservoir. A first law of balance would tell you that the work obtainable from this irreversible heat engine, you can get that just from a first law of balance. Then imagine another heat engine. Okay, so again, you are getting same amount of QH, but a different amount of heat is being rejected. Because if you get more work, okay, again, by first law of balance, you can connect the work of a reversible heat engine to QH and QL reversible, right? So this can be, this connection can be made by first law. So what is that? We are here, let's say, hypothetically, the efficiency of the irreversible engine is greater, right? So if that efficiency is greater, that means work obtained from the irreversible engine is greater. Therefore, the heat that is rejected to the low temperature reservoir by the irreversible heat engine is lesser, okay, compared to the heat rejected by the reversible heat engine. Okay, so that's one part of the statement, okay, one part of the proof. Let's see how we are going to elaborate further. So here, notice that we said this is a reversible heat engine. So what is so special about a reversible engine? Every process can be reversed, okay? So for example, if you reverse this heat engine, it becomes a refrigerator. So what is a refrigerator? It takes up heat from a low temperature reservoir. In this case, it takes up this much amount of heat, QL reversible. It takes from the low temperature reservoir, and then there is a work input. Okay, this has been reversed. Instead of work obtainable from a heat engine, this is a refrigerator. R denotes a refrigerator. There's a work input into the refrigerator. Again, a first law balance would tell you that QH is the heat that is given to the high temperature reservoir. So what does a refrigerator do? It takes up heat from the low temperature reservoir. Utilizing the work input, it transfers heat to the high temperature reservoir. So what we can imagine is that we can combine the irreversible heat engine, this generates work, with the reversible refrigerator, and this combined process can be represented in the following manner. Okay, so what is to be noted is QH is taken out by the irreversible heat engine, but the reversible refrigerator transfers QH to the high temperature reservoir. Okay, so there is this QH is cancelled by this QH. So what do you get? So what you get is that you get net work of the order of W irreversible minus W reversible using just the heat exchange with just the low temperature reservoir. Okay, so how much is the heat that is obtained from the low temperature reservoir? That is equal to QL reversible minus QL irreversible. The entire, this amount of heat is transferred as work. Okay, it is obtained as work. Okay, so what is the problem here? So this is a violation of Kelvin-Planck's statement of second law of thermodynamics. Okay, so again, so what this proves is that this is not possible. That is, the efficiency of the irreversible heat engine can never be greater than that of the reversible heat engine. Okay, so this is just a logical argument. Using that, we have demonstrated that it is always the reversible heat engine has a greater efficiency amongst all possible heat engines. Okay, so what we are contrasting it against is the irreversible heat engine. Okay, so note the efficiency measure of a heat engine for the same amount of heat that is transferred from a high temperature reservoir. The efficiency measure is the amount of heat that is rejected to the low temperature reservoir. Okay, so this combined device violates the Kelvin-Planck second law statement. Therefore, it is impossible. Again, this is a non-mathematical statement. It is just a logical statement. I want to emphasize that. Okay, there's a power of logic here. And then you can imagine another device, another thought experiment, in fact, thought device for proving the Carnot second principle. What is to be proved? The efficiency of all reversible heat engines operating between the same two reservoirs are one and the same. Okay, it doesn't matter whether the engine fluid is air or water, the efficiency has to be the same. Okay, so it's this proof is easier having proved the first principle. You can imagine, let's say there are two reversible heat engines, but one having greater efficiency. In this case, both the heat engines have same efficiency. What does that mean? Okay, so let's say we fix this. If the efficiency is the same, what does it mean? That the heat rejected to the low temperature reservoir is one and the same. Okay, so just fixing the temperatures here fixes the efficiency. But supposing one of the reversible heat engines had greater efficiency, what can you do? You can reverse that heat engine into a refrigerator, and then you would see that the amount of heat that is rejected to the high temperature reservoir is the same, right? I mean, there is a reversible heat engine, and there is another heat engine which has been reversed to become a refrigerator that is delivering QH to the high temperature reservoir. So the amount of heat taken by one heat engine is the same as the amount of heat that is delivered into the high temperature reservoir by the refrigerator. So that part gets out. The combined device effectively would convert heat from the low temperature reservoir into work. Okay, so that again is a violation of Kelvin-Planck's statement of second law of thermodynamics. Okay, second law of thermodynamics. So again, using a logical proof, Carnot was able to state that all reversible heat engines operating between the same two thermal reservoirs have the same efficiency. So again, what is to be noted? Whenever you say one heat engine has greater efficiency, okay, so what is lesser? The heat rejected in to the thermal low temperature reservoir is lesser. Okay, that's a crucial proof, crucial thing to notice for proving just via logic Carnot's second principle. So next thing to understand is we're talking about cycles, right? So what exactly do you mean by cycle? We addressed this in the first few lectures, first few chapters of this course. So when there's a fluid that is undergoing a thermodynamic cycle, you may start at one point. There are a variety of processes that can occur that this fluid may do work, may accept heat, reject heat, work can be done in a fluid. All these things can happen. Eventually, it has to come back, okay, in the state space, okay, in the thermodynamic state space. Here, the thermodynamic state space is represented in the PV diagram, pressure, specific volume diagram. It has, after undergoing all the processes, it has to come back to the same point, right? So eventually it's something like a circle. And what Carnot succeeded is how to represent a thermodynamic cycle using different processes. Okay, so this it's a great creative achievement. Okay. So let us see what are the four processes that Carnot used for getting fluid to the same state after it has seen different processes, okay? Work generating processes, heat transfer processes, and so on, okay? So there are four processes. In the first process, let's say 1, 2, you have an isothermal, that is the temperature is TH, that's not changing, it's isothermal. It is accepting heat from a high temperature reservoir and it is undergoing isothermal expansion. Okay, so there is heat transfer from a high temperature reservoir. It is a reversible heat transfer, okay, mind you. Okay, so it accepts heat and expands, but the temperature remains a constant, all right? So just to build your intuition, always imagine all these things occurring via ideal gas, okay? That's not a necessity because we earlier stated, we proved by the Carnot second principle that all this Carnot analysis is independent of the fluid you use, okay? So if it is independent of the fluid you use, you can use an ideal gas to build your intuition and for further mathematical analysis, which you would see in the next couple of lectures. So here in the first process, 1, 2, it is an isothermal expansion by accepting heat from a high temperature reservoir. The next process is 2, 3. Here in this process, we are insulating this piston, and what we are having is an adiabatic expansion, okay? Because of adiabatic expansion, the temperature decreases from TH to TL, okay? So here TH is the high temperature reservoir temperature and the TL is the temperature of the low temperature reservoir, okay? So you are at 0.3, right? So then again, you remove this insulation, facilitating heat exchange to a low temperature reservoir. So you give off some heat, so but the temperature is the same. It is still TL. It's an isothermal compression, compressing the volume from this point to this point, right? So it's an isothermal compression by rejecting heat to a low temperature reservoir. Again, in the fourth process, 4 to L, 4 to 1, what you have done is you've insulated this piston again, and then there is adiabatic compression. Okay, so this adiabatic compression, what it does is that it increases the temperature from TL to TH. All right, so this is a way of representing a cyclical process. Okay, so there are two isothermal processes involving heat exchange, and there are two adiabatic processes without heat exchange. What have you achieved by doing that? Okay, so you come back to the same point. Okay, so that you have accomplished a cycle. Okay, cycle, you have to start, undergo different processes, and come back to the process. So you demonstrated at least there is one way of implementing a cyclical process, a thermodynamically cyclical process. I mentioned all this process is a reversible process. Okay, so that is the temperature here. Temperature difference is infinitesimally small. Temperature difference is infinitesimally small. These expansions and compressions are quasi-static. Okay, they are reversible. Okay, so what is the power of such a process? You can reverse entirely. Okay, so every process can be reversed. Okay, so if it's a heat engine, if this is a work generating heat engine, there is effectively net work output. Okay, so why should there be, just to backtrack a little bit, why should there be a net work output? Okay, so what is the work here? Okay, that is PdV, area under this integral, and then there is this another PdV process. Okay, so there is, you can subtract, we will see this in the we will see this more closely, what is the amount of work you get, okay, in the next couple of lectures. But eventually you will see that you will get net work out of the system by integrating area under the curve. This is the net amount of heat, net amount of work that you get by operating this reversible heat engine. You can also operate this in the reverse and have a reversible refrigerator. Okay, this refrigerator takes up heat from a low temperature reservoir and transfers heat to the high temperature reservoir with some heat input. Okay, every step is reversible in this. Okay, so there's an arrow that takes you from 1 to 2. Here, this arrow is in the opposite direction. It's 4 to 1, and so on. Every process is this reversible heat engine. Every process is reversed here. You have a reversible refrigerator. All right. Okay. So we have implemented a thermodynamic cycle via a piston cylinder. Okay. So is this restricted to this? Because this is not as general structure that you have seen from power cycles. Okay, in your previous lectures, previous chapters of this course, you had seen different power cycles that had different kinds of structure. Okay, so you will see that Carnot's analysis and Carnot cycle is not restricted to a piston cylinder. You can have Carnot vapor cycle too, right? What exactly do you mean by that? Okay, there's a boiler which evaporates from a condensed phase to the vapor phase by a heat input from a high temperature reservoir. That vapor is used to run a turbine and get some work. Then again, there's a condenser when there is condensation process, new bonds are formed. Because of new bond formation, there is a heat release, and this heat released is given off to a cold reservoir. Then a pump is used to pump the liquid from the condenser to a boiler. So there's work input here, okay? So there can be phase change here. So this goes beyond piston cylinder, and this Carnot vapor cycle can be represented in the PV diagram again. So we've already seen how to represent all these processes in the PV diagram. So there is two isothermal processes here, TH and TC, and these 1, 2, 3, 4 corresponding to these points can be represented in a PV diagram. Okay, so the power of this analysis is enormous. So this is going to be utilized for analyzing real power cycles and so on. Okay, so where do we go from here? Here we demonstrated that the efficiency is of a Carnot cycle, Carnot reversible cycle, is just dependent on the temperature of the high temperature reservoir and the temperature of the low temperature reservoir. Okay, so this has utility beyond heat engines and refrigerator. It is used for establishing a temperature scale that is independent of the thermometric fluid. Okay, so that's what we are going to see in the next class. Thank you.